as old as my stay in IIT. I have been teaching many subjects. So can you individually introduce yourself? Raja is there. Raja is it our own Raja? Unmute. You please unmute the mic and say something. Is it Raja Manikandan? Is it Raja? Okay. While he's answering, Raman.
Hello, sir. My name is Raman.
Yeah, tell me a little bit about yourself. Where are you studying?
Sir, I come from Pondicherry.
Okay.
I completed my BSc Chemistry in St. Joseph's College, Kadalur in 2020. Yes, right now I'm preparing for entrance exams for first 2 years. Okay,
so you are also doing for GATE examination or something like?
No, sir. I just completed my BSc on 2020.
Okay, so you have not done your MSc. Okay.
No, sir. I am preparing for entrance exams.
Okay. Do you think this course is useful to you?
Yes, sir. Yes, sir. So,
okay. So you have to tell me more about it when we have further discussion. Okay.
Yes, sir.
Let me request Ilavarsi. Can you speak? Unmute the mic. Your mic is muted, so please unmute. And then there is Sandeep Kumar. Okay, Ilavarsi is not coming yet. Sandeep Kumar, yes, please go ahead, Sandeep.
Yes, sir.
Yeah.
Sir, myself is Sandeep Kumar. Actually, I have done my master's from IIT Kharagpur, sir. And after, actually, I have done my master's from IIT Kharagpur, sir.
Jodhpur, okay, okay.
Yes,
are you the one who were working with Atul?
Yes, sir. No, sir, I'm not, sir. Sir, I have done my master from IIT Kharagpur, sir.
You said IIT Jodhpur, right?
No, sir. It is Kharagpur, sir.
Okay. Okay. And
after that, I worked for some like companies like ONGC and
okay.
And now I have quit that job, sir. So I want to pursue as a lecturer position, sir. So for that, I have to appear for NET and GATE examination, sir. So,
so you are also
that NET exam. Yes, sir.
Preparing for GATE and
NET exam, sir. Yes, sir.
Examination.
NET exam, I shall be.
You think this course
so that I can apply for the lecturership position.
Faculty position, that's right. Yeah, lecturer position you can. And if you get a fellowship, you can actually also go for a PhD, right?
Yes, sir. Yes.
Okay.
Yes, sir.
And Ilavarasi, are you able to speak now? Can you unmute the mic? No. Okay, she's listening, but she's not. I don't know. Raja?
Sir.
Oh, that's you. It's our. Hello?
Yeah, Mr. Manikandan, sir.
So where is Madhu? I have not seen him. Oh, he's IIT Madras.
No. I think Madhu might have network issues, sir.
Okay, no network issue. He's having problems. That must be Balaji. Okay, are there any questions? See, the whole meeting is, if you have specific questions and you want to ask anything about the doubts, I will be quite happy to explain. Would you want to go ahead? Anybody in the YouTube, if you want to chat?
Sir, my name is Raman. Can I ask a question, sir?
Please do. Yes.
Sir, I have two questions.
Yeah.
The first question is, I want the answer as a physicist or a chemist, not as a mathematician. Okay. So can you please explain why the wave function is a column matrix? That is the first question, sir. Okay. The second question is, in the second lecture of the first week, you explained the basic mathematical functions such as Gaussian type functions. Okay. But in the IR spectrum, usually in computational chemistry packages, I usually see a IR spectrum as Lorentz fit or Gaussian fit. I tried to relate it to the Heisenberg's uncertainty principle, as frequency is actually related to the energy index, and which is the Fourier transform is like the time. So E and T or the Heisenberg's and it actually fits into the Heisenberg's uncertainty principle. Therefore, in case of Lorentz fit, the area under the curve is actually less, or I don't know how to say that, sir, but it is actually steep. But in case of Gaussian, it is actually a bell shape. So there is a wider IR fit. So therefore, I think that Lorentz can be more useful than the Gaussian type fit in the IR, sir. Sir, I have these two doubts. Yes, sir.
So the second question, I'll come back later. First question is about why is wave function a column matrix? Is that correct? The first question is, why is wave function written as a column matrix? Is that correct, Raman?
Yes, sir. Yes, sir. Yes, sir.
Yeah. So let me first share my screen, okay, so that you can see what I have, so that you can see a notebook, okay, in front of me. So the wave function, there are three ways of doing it. The wave vector or an operand. It's a, what do you call it? It's an abstract quantity. Every system is associated with a psi. Let me start a new page. Okay, psi. Can you see what I'm writing?
Yes, sir.
Yeah. So every function, every system is, the objective for us is to solve either the time-dependent Schrodinger equation, time-independent Schrodinger equation, and get a psi, which is an eigenfunction, or time-dependent Schrodinger function, which is slightly different because it has time in it. Now, this is abstract, okay? Abstract in the sense, see, for example, if you remember vector, only when you associate with vector some components, x, y, z components, you can physically visualize a vector in 3D, three-dimensional world, right? As pointing in this direction or that direction. Otherwise, you will simply say vector as pointing in some direction and has a magnitude. Those are the only two things you can talk about. How do you represent vector in a real situation? You associate a coordinate system, right? And then project the vector in the coordinate system. And then you can say that this is the x component. Then you can do that. Sorry, this is the x component, this is the y component, and this is the z component. Okay? This is what you do. So the three components that you write for a vector A in terms of x, y, and z as the components AX. Let me see. This is a new tablet I'm using. So let me, AX, AY, AZ. This is a representation in coordinate system. In coordinate system for the vector A. Vector is something which is abstract, something which has a certain direction and certain magnitude. Okay. Now, the magnitude, how will you get? You will get by squaring all these things, adding them up, and then taking the square root. Therefore, you can say that the magnitude of this vector can be given by these components. How do you get the direction? You get the direction in terms of, for this vector, of course, it's three-dimensional. So there are usually three angles you need with respect to the axis system x, y, z to say that this is precisely how the vector is. Those are representations. Why am I saying this? Because the wave vector psi is represented in a matrix is one form of representing the wave vector in terms of its components. Okay, suppose the wave vector psi for a particle in a box. And let's take a simple system, not even particle in the box. Let's take that the system has like a spin a half system, a spin one, spin a half system has two possibilities, a plus half and a minus a half orientation in the magnetic field. This you are very familiar with, right? Which you call as an up state and you call this as a down state. Therefore, now these are two basis functions, which when you measure, you get the corresponding the spin wave function of this, which is given as a component times a plus a half and a component times a minus a half. And these components are what you do not know, and therefore you are trying to represent them. So the representation of a wave function in terms of a matrix is a form of organizing them so that you can do the computational process as that of all the matrix algebraic processes. Originally, the wave function as a matrix, position and momentum coordinates were originally written down as very long columns, infinitely long columns by Heisenberg, with the elementary association like what we have here. In two dimension, if we have two unit vectors, we represent them by a two column vector. Okay. In three dimension, the unit vectors, we represent them by a three column, 3 rows, 3 column, 0, 0, 1. Okay. So then what you need to do is the algebra of these vector components, or what is called the directions or basis elements, is to follow faithfully the algebra of the matrices. So when you want to say x dot y on the page, when you say x dot y, you know it is 0, isn't it? When you say x dot x, it is 1. How do we represent this using this column? So if you have to do a function calculation and if you have to do a matrix calculation, the one-to-one transformation happens when you write the x dot as a row matrix, essentially x transpose multiplied by y, which is 0, 1, and that when you do the matrix multiplication, it is 0. Okay. And if you want to write this, the matrix multiplication for this is 1, 0, 1, 0. It is x t dot x. Okay. And then you get 1. So the representation of a wave function using matrices is in terms of what are known as the basis functions. In the case of a spin 1/2 system, it's two basis functions, a plus basis function and a minus basis function. The plus basis function can be represented by 1, 0. And then the minus will have to be 0, 1 because these two basis functions are orthogonal to each other, plus and minus states. And in matrix, the orthogonality comes through the corresponding matrix product. Therefore, the representation using matrices is 1-to-1. If, for example, a wave function can be expanded in terms of many basis functions. In the case of hydrogen atom, you have infinitely large number of basis functions, 1s, 2s, 2p, 3s, 3p, 3d, 4s, all these things. Therefore, what is meant by a matrix representation? Each basis function is an infinite column. It's an infinite number of rows, one column with only 1 in one of them and zeros everywhere else. So depending on the dimension of the physical dimension of the problem. Okay, how many basis functions are required to determine uniquely a wave function in terms of these numbers A, B, C, etc. That dimension determines how we represent them in matrices by the corresponding number of rows in a given column, like what you have. The number of rows here is 1, 2, 3, because this is a three-dimensional, and any vector can be expanded in terms of the components in these three directions only, as the sum of these three directions only. Therefore, this is enough. Whereas wave functions can be represented much more generally by matrices. Wave functions are like vectors. Therefore, vectors are represented by columns. Now, operators are not like vectors. Operators are, if you think about the operator, an operator acting on a function giving you a constant times a function. This is an eigenfunction. But in general, the operator acting on a function may not necessarily give the same, but it may give 5. Now, please remember, this is a column and this is a column. The linear algebraic process tells you that A has to be a matrix, which is such that the dimension of the matrix is such that the dimension of the matrix is the same as this, and it is given by m by n. This has to be n, and what you will get, m by 1. If m and n are the same, obviously n by n times n, you will get that. The operators are represented therefore by square matrices for all the practical purposes. We will not worry about rectangular matrices in general for this course, but square matrices, and the square matrices multiplying the columns wave functions give you other wave functions, which is again a column. If these two columns are identical and there is a constant, then we say we have an eigenvalue for the matrix. Okay. So these are, unfortunately, these are mathematical representations of a physical system, and psi is not a physical quantity. Psi is a measurable number, real quantity. Psi is a property of the system that we try to get. Therefore, don't attach too much meaning to psi. Psi can be, wave function can be a complex quantity. We normally do not determine the wave function experimentally. Cannot. We can only find out the probabilities for the system which are given by psi star psi. Okay, this is question number 1. Now, the second question that you asked, can you repeat the question very quickly? Sorry, because of the long.
Yes, sir.
Yeah.
So the significance of Lorentz over the Gaussian in the IR spectrum.
No. See, first of all, line shapes, when we measure experimentally, we find out that a broader line shape is usually fit by a Lorentzian. A narrower line shape is usually fit by a Gaussian. Okay. The reason for that is also you have to go back. Gaussian and Lorentzian line shapes are functions which depend on frequency, right? You are plotting frequency on one axis and then the intensity of absorption on the other axis. Another page. You are plotting the, let's do it this way. This is the frequency or omega, if you want to write omega, and this is the intensity. And so if you want a Lorentzian, it's something like this. And if you think of a Gaussian, it's generally, it is much narrower because this is an exponential minus some constant times omega square. This is like a constant divided by some a square plus omega square. Okay. What is the origin of these things? The origin of these line-shaped fittings come from the decay times for the energy levels. You said rightly that the energy and time are Fourier transforms of each other, right? That's what you mentioned. The energy of a system. Suppose a system is very stable. It does not, it stays in the energy. What is its lifetime? It's very long because it's stable. It stays there. Therefore, the lifetime is very long. It's not the energy of the system that is directly related to the time. There are two things. When you use position, momentum, uncertainty, it is very clear. Measurement of position and measurement of momentum have uncertainties associated with them. The uncertainty in the position and the uncertainty in the momentum, their product cannot be less than h bar by 2. It can be, experimentally, it can be higher. But if you bring down to the best of the experimentation and you go to ideal levels, the lowest level of that product, lowest value for that product is h bar by 2. In the case of energy and time, it is not like that. It's the lifetime of a species which is in an excited energy state. Please remember, suppose the system gets excited to an energy from, say, this is the ground state. And this is the excited state. Okay? Though we write the excited state as one energy, the excited state has a spread in energy. Okay? This spread is called delta E, which is the uncertainty in the energy of the excited state. The lifetime of whatever has gone in here, in this spread of energy, if you call it as delta T, that's tau. Okay? Then delta E, delta T is greater than or equal to h bar by 2. This is the basis. Okay? Therefore, now, if a species lives very long in the excited state, and when you try to do the absorption, excitation and absorption, what happens is the spread in energy is very large. The spread in energy is very small. It's because it stays there in the excited state for a fairly long time, which means it is very precisely located in energy. For such a system, the line shape will be a very narrow function in energy, in frequencies. If the line shape is almost like this, very short, what it means is that the uncertainty in the measurement of energy is very small, excitation energy. Therefore, delta E is extremely small, which means the lifetime of the species in that state corresponding to this excitation delta T is very large. Okay? Such the product is still greater than or equal to h bar by 2. So this is what is meant by the line shape. And if there are no disturbances from the external system, if there are no disturbances due to molecules hitting each other, a molecule is excited on its own through the absorption of radiation, then what we call this as the natural line width. What is called the minimum line width that is required, that is connected with the lifetime of the excited species. Therefore, every excited species has a minimum certain spread in energy. Very highly excited states have a very large spread in energy, and therefore their lifetime in that energy state is very short. And so you can see if delta T is extremely large, delta E is extremely large, delta T is very small. And so you can see that this is the relation that you can have. Lorentzian and Gaussian processes are dependent on the decay of the excited states.
It's 17 hours.
Hello? Yeah, the decay of the excited states. If the decay is exponential in time, okay, the excited species in time at a certain, this is time, the excited species sort of decays like this exponentially. Then the exponential decay, when it is Fourier transformed with respect to the spectrum that the excited species produces, you will see that the exponential function, the Fourier transform of that gives you the Lorentzian. If the excited species decays very fast in a Gaussian form, you will see that the Fourier transform of the Gaussian form, which gives you the frequency spectrum, okay, is also Gaussian. So, but please remember, what you are plotting here is what is known as the correlation function related to the excited state. And the Fourier transform of the correlation function is proportional to the power density, which gives you the spectrum, and therefore the relationship between a time domain signal, which is plotted as a correlation function, autocorrelation function here. That autocorrelation function has a Fourier transform, which is the spectrum. This wasn't very long ago. This was demonstrated by a mathematician, and also many experiments have been done. The very famous experiment being done in the early days was the NMR experiment by Irving Low and Norberg in Pittsburgh in 1957 or around that period. And then there are many experiments which demonstrate that the Fourier transform of the decay process given by the autocorrelation function, which is a statistical quantity, you have to calculate that, gives you the spectrum. And whether it is Lorentzian or Gaussian is also dependent on whether the decay process of the autocorrelation function is exponential or Gaussian. Now, why are these two? Why not the other functions? We don't know. I mean, there can be other functions. It is not necessary that we have to fit a spectrum to a Gaussian or to a Lorentzian. We may be able to fit it to a polynomial. Those are special cases. Largely, systems which are, in the normal measurement, systems give you either of these as the measurements that we can make. So, I don't know. Does it satisfy the sort of things that you were looking for? Does it give you?
Yes, sir. Yes, sir.
Partly. Okay.
Sir, but why the computational packages allow choices? Actually, the AR spectrum can be given in both Lorentz and Gaussian. Why they give choices?
Okay. The choice is because you do not know what the experimental system results would be. So computationally, you should be able to fit the experimental results that you get to either this or that. Therefore, when you do a computation, you should have all possible outcomes, because those are theoretical outcomes. Please remember, okay? Experimentally, if you see a spectrum which is Lorentzian, then you must fit your computational results to a Lorentzian. So until then, you do not know whether it is Lorentzian or a Gaussian, but you can guess depending on the similar properties of similar systems. You can expect the decay process, the line shape to be probably Gaussian because you have some experience in that. But computationally, I cannot give you a package which will only tell you how to fit a Gaussian function. Okay? Which one do you choose is partly dependent on what information do you also have as an experiment. So fitting the experiment to a Gaussian function or a Lorentzian function will tell you clearly whether computationally you can also reproduce that result for those transitions. So packages should give you all the options to calculate, but the user should diligently choose what is the correct option or what is the appropriate option based on some preliminary knowledge. Okay. Packages cannot give you, see, if I have a package which can only fit it to a Gaussian, and I have a physical system where experimental measurements give me an exponential decay, that package will be useless to me, isn't it? Because I can't use an exponential fit to a Lorentzian in frequency space. I can't do that. The Fourier transform of a Lorentzian is an exponential. The Fourier transform of an exponential is a Lorentzian. Therefore, it is important that we have computational facilities, but the computational outcome is that of the intelligence of the user with the information that he or she already has about the practical experimental systems. So you have to worry about that, okay?
Yes,
Next.
sir. Yes, sir.
These two are very good questions. I would not have expected them from the first course, but surely some of you have been looking at, there are many more. So 2 or 3 more people have joined. Let me see. Sneha Patil has joined. Sneha, would you like to say something about yourself? Unmute the mic, please. Yeah, please go ahead. I'm able to hear. Sneha? Okay. We'll wait for you. Sandeep Kumar has already spoken.
No, sir.
This is my own PhD scholar. He writes to you often. Subhadeep, did I talk to you earlier?
Yes, sir.
Yeah, go ahead.
No, sir. Okay. Sir, am I audible?
Yes, you are. Yeah.
Sir, I am an undergraduate student at Presidency University with chemistry honors. I'm from Kolkata.
Sorry, which university?
Presidency. Earlier it was Presidency College.
Yeah. Presidency
Under Calcutta
University. Okay.
Yes, sir. And I have I have interest in particularly in atomic structure and chemical bonding this chapter. So I actually joined this course, and we are also studying the same thing, but obviously at a very different level, qualitative level. Then here we are actually dealing with all the things that you have taught us, the Hermitian operator and others. But in our university course, we are qualitatively dealing with it.
Yeah, that is okay. That's the way it is. This is for you to learn on your own and with the help of online sessions like this and problems and so on. I cannot cover any particular university curriculum because then that will be different from another university and so on. So I give you a broader, what I call as a fairly necessary detail if you go to 3rd year or a first year MSc and so on. So that's good. I hope you find the contents useful to you.
Yes, sir. Very much useful. I enjoyed it a lot.
If you have any questions, please raise. There are others who can. Sneha, do you want to say something about yourself? I'm not able to hear you. Okay, there was one more person. He just left. Disconnected. Okay, are there any other questions? Would you like to? I would see, I've already given you enough lectures, 52 or something like 55. So I don't want this to be a lecture session. I want this to be a session in which you would interact with me on specific things and things that you find in textbooks, things that you don't understand in textbooks, things which are relevant to you. Why do we need to study these things? I think a lot of these questions you have to ask. I don't say all those things in the lecture because the lecture is focused on. Yeah, go ahead.
Like they have asked in the forum, they asked some 2-3 questions. I'll post the question in the chat.
I've not seen the forum yet. Yeah. What is the question?
Yes, sir.
In chat box, I have sent you the questions.
In the chat box, let me look at the chat box. Yeah, okay. There is a question here. Yeah. In the question number 4, week number 3, assignment 3, the unit vector associated with the column vector 3, 4, 5, 3, 5, 4, the given answer options are not matching with the 3rd element. Okay, let me see. Do you have the question, Raja, Bani or Madhu? You want to post it up? I'll allow you to share the screen. Oh, sorry, I'm not under control. Technology has to allow the people to share the screen. Madhu, put the question up.
Madhu, I just give the access, Madhu. You can share also now if you can.
Sorry?
Sir, I gave the access, sir. Now they can share the screen.
Yeah. So Madhu, share your screen with that question. I just want to see what that is.
Yes, sir. I'm sharing.
Yeah. Thank you, Sneha, for the information that you have shared on the chat box. Yeah. So the question is in 3, 5, 4, that's a column. The given answer options are not matching with the third element. Yeah, just tell me that question. Move up to that question. I don't know if I made a mistake. Let me just check that. Okay. The question, the unit vector associated with the column vector 3, 5, 4. I think there's only one answer. The answer is, see, you have to absolute square of this 3. You have to take the absolute square of 5i, which is 25. And this is 16, so it is 50. So square root of 50. And you must ensure that these elements are not changed. So you are right. I mean, 3 of the columns don't even match. So you can throw them away right away. Okay. The given answer options are not matching with the third element of the given unit vector. What are the options? A, B, C. What is D? Can you go up to D? Okay. 3 by 50 minus 5i by 50. See, you can see that this option is not matching with the question. 3, 5i, 12 is also not matching with this. I think the answer is very simple. You are not supposed to give the answer, Madhu.
Sir, actually, I asked the question, sir. Here, the probably the unit vector is having 3, sir.
Say it again.
Sir, actually, its mod is coming a square root 50, sir. A square root 50.
It's mod. You have to do only the modulus. Yeah.
Yes, sir. Modulus is coming a square root 50.
Yeah.
But the option given, sir, option given is not matching, sir. We can see, sir. We can see in the option is 12, sir. Instead of 12, the option should have been 4, sir. We can see the third part of the unit vector, sir. For me, the answer was coming C, sir. But here it should be 4, sir. Instead of 12, it should be 4.
Which should be 4? I'm wondering. This one.
Here
yes,
it
sir.
has
Yes,
to be
sir.
4.
Yes, sir.
So that's
yes, sir.
Yeah, if that's what you are saying, that's correct.
Yes, sir. Yes, sir.
The question was wrong.
Yes, sir. Question was wrong, sir. Yes.
Graphical error. Yeah, that's fine.
Yes,
I
yes.
made. Yeah, that's correct.
Okay.
Thank you. How to check whether the linear combination of a projection operator will be a projection operator or not. The only way to check whether an operator, okay. Yeah, so let me share that. The only way for a projection operator to be is P square is P. Suppose P is a constant times an operator A1 and another constant times an operator A2. You must ensure that P square also gives you, which is A square A1 square plus A2 square A1 square, A2 square, A2 square plus A1, A2, A1, A2 plus A1, A2, A2, A1. Okay. Now, this should reduce through the properties of the operators to A1, A1 plus A2, A2. Generally, this will not happen. Therefore, if you take two projection operators, suppose P1 is a projection operator and P2 is a projection operator. And then there is something which is remaining, which will all add up to give you what is called these are all normalized projection operators, so it will give you 1. Now, please remember P1 plus P2 square is P1 square plus P2 square plus you can write 2p1, p2, or you write p2, p1, but then unless p1 and p2 are orthogonal to each other, okay, this will not go to 0. Therefore, this has to be orthogonal. P1, P2 should be orthogonal, giving you 0. Should be 0. And then P1 square is a projection operator. P1 is a projection, therefore P1 square is P1. P2 square is P2. So it's possible. Okay. So you have to make sure that the projections are orthogonal to each other if there is a linear combination. But then the problem is, if you have coefficients, the coefficient squares will not match. See, ideally, I have chosen a coefficient of 1 so that 1 square and 1 square give you 1. That's a cheating. Okay. Therefore, in principle, a linear combination of projection operators without any numerical coefficients can always be a projection operator if all the individual projection operators are orthogonal to each other. If they are non-orthogonal, the linear combination will not be a projection. Does it make sense?
Yes, sir. Yes.
Good question. Very, very good
Yes.
question. Thank you. Now, any other? Yeah. So this is correct. Okay. So this, I think, that's the result. Vij is valid for any multiplicable vector operator.
No, sir, that is big chat, sir. You need to read from.
That is your question.
Not my question, sir. They have posted in the forum.
Oh, it was posted in the forum. Okay. So let me
Yes,
read.
it is my question, sir. My questions.
Have you answered it?
Yes, sir. I'm saying, sir. I'm saying what I wanted to ask, sir.
Vij Vi star is always for the vectors, irrespective of whether the vectors have complex coefficients or real coefficients or a mixture of them. This is the definition of the scalar product. Okay.
Yes, sir. But sir, is there any condition that these vectors Vi and Vj should be a column vector, or for any vector, sir, it is
Number
applicable?
Vi Vj, the product Vi Vj is a number. The product Vi Vj, the scalar product is a number. It's not a column vector.
But the individual matrices, sir, Vi matrix and Vj matrix.
Okay. Now I think I see what you are saying. The Vi is not just the column vector transpose, but it's also complex conjugate transpose, the bra vector. Okay. Let me tell you. I'll give you an example. Yeah. So suppose you write Vi Vj, and you write this as Vj Vi star. Suppose Vj is A1, A2, okay? And this is the column. The column Vi is B1, B2. Therefore, the row Vi or the bra vector is not B1, B2, but it is B1 star, B2 star. Complex conjugate transpose. Transpose. This is the definition you should remember. Vj, sorry, this is Vj is this, yeah. So Vi is this. Now, you can see immediately that this product Vi Vj will be B1 star, B2 star, A1, A2. Okay. The product Vj Vi star will be, please remember, Vj is now the complex conjugate transpose. So this will be A1 star, A2 star, and VI is just to the column B1, B2, but the whole thing is complex conjugate. Both of these are equal. Okay? Both of these are equal. Does it make sense?
Yes, sir. Yes. Yes.
That's all you have to be. So this is a definition. The top line is a definition of the scalar product. The only thing is the scalar product for the bracket on the left-hand side, what is called the bra state, and the right-hand side ket, the relation between the two is that if one is a column, the other is a row, but with the elements complex conjugated. That you cannot forget. If you forget that, then there will be an issue like what you pointed out. Okay?
Yes, sir.
Yeah.
Sir, for this bra and kit vectors, so is it necessary that this bra vector and kit vector should be that kit vector specifically, it should be a column vector, or it can be a 2x2 matrix also, sir?
No. The bra and ket vectors will always be columns.
Okay, sir. Okay, sir.
The vector is always a column.
Yes,
The
sir.
product is always a number. Okay?
Yes.
Suppose right, for example, just here I had a page. Let me write. Suppose I have a VI, an operator A, Vj. Okay? Let's write VI as A1, A2, Vj as B1, B2, and we write the operator A as a 2x2 matrix, so we will call it as A11, A12, A21, A22. It's a matrix. So how do you form this product? You form this product by forming VI in the bra state. Please remember, the relation between these two is you already know. It is A1 star, A2 star. Okay. What is A? A is the operator. A11, A12, A21, A22. What is Vj? This one. B1, B2. You see, the product will be a number. It's not a matrix. Because it is 1 by 2, 2 by 2, 2 by 1. This will go away, it will give you 1 by 2. This will go away, it will give you 1 by 1. Okay? So, scalar products are numbers. The expectation values are numbers, but the quantities which lead to these things are vectors and operators. Okay? That's what you should remember. Okay, any other question? Does it make sense?
Yes, sir. Yes, sir. Yes.
So the association, so the first question when Raman asked you, why do we put vectors into columns and so on? See, the linear algebra directly tells you that that is a very nice representation. And today, writing all these things using matrices, the numerical calculations involving matrices is so straightforward. Okay. If you have to write the wave function and you have to write the integral of the wave function and then calculate the integral very accurately and so on, it's going to be a problem. But you still have to do part of it because each element of that matrix, for example, the matrix of operators, each element itself is an integral of some kind. So somewhere along you have to calculate them, but you stop at a very low level. And these are in quantum chemistry, these are usually known as the 1 electron integral, 2 center 1 electron integral, 2 center 2 electron integrals. Those are the basic computational elements that you need, but the entire calculation for the expectation value for the energy is all done using matrices, because numerically the linear algebraic processes in the computers are much, much more advanced and much, much more robust. And packages are available today to do the diagonalization, to do these matrix multiplication of large numbers. You don't have to do any of them by hand. Whereas numerical routines for calculating functional entities like integration and differentiation and finite differences, they are more involved and they cannot be scaled to a very, very large amount like in the case of matrices. That's the reason why we use matrix representations today for practically all the quantum calculations. Okay. Any other question? So I hope you don't have any complaints regarding that. That mistake has to be corrected. Okay, problem 3, we will remember that. I don't know how it went through, but other than that, I think you are you comfortable with the level of lectures, the speed, the amount of content? Do you find that the lectures are more demanding in time and you can't follow them as spoken, but you need to go back and do it? What do you find? The lectures are okay in general, or you have to listen to the lectures again? What is
we have to listen it again, sir, because it is good to listen it again, because one lecture is connected to other lectures now. So we have to listen it again, sir.
Yeah, you need to go back. No, yes. I have made it more than what normally a first or second year college level course would give on these things. If you go back to other universities, the first and second year courses are usually much lighter than this course. But the whole idea is, I think you want to learn. Something should be spoken very, very clearly. And something should be driving you to learn rather than, oh, I listened to the lecture, I understand everything. That's good. It doesn't happen always. But a lecture should always leave you with things that you don't understand and you are always worried about. And that's, in my view, I think at the level at which I'm dealing with, this is easy for an MSc student, but this is a little tough for those who are doing their BScs and particularly in the third year looking for JAM examination. This will be very useful if you want to study for JAM, at least this part of it. And likewise, other NPTEL courses, some of them are very useful for you. And also for GATE, some of us, okay? Okay, I hope that all of you are safe and you are not. How many of you are actually going to the university now? Two or three, if Sandeep is going. So you can just put your hand up in that. You can see the hand sign. So if you do that, I know. Then one of them is studying from home and a couple of others said they are studying in colleges. So please be careful about your health. And the times are very difficult. Corona is not something that you can, I mean, even I am, for example, today I'm lecturing from home. I'm not lecturing from my office. I go to the office only when it is required. And we don't have classes offline yet. We still have all our classes are online. Please take care of yourself, okay? Continue to study. We will have we'll schedule another meeting on Saturday.
Sir, I have one more question, sir. One question.
Yes, please.
Yes, sir. Like, sir, we are actually we are representing the operator matrix with the help of our projection operators.
Okay.
We are representing the operator matrix using projection operators. But among the projection operators, sir, only few operators, actually few of the projection operators are orthogonal, sir. Orthogonal.
See, position operator is, I didn't quite follow the question. Can I repeat again?
Sir, actually, it is about the projection.
Projection. Sorry, not.
Actually, it is about the. Yes, sir.
Projection operator.
Question.
Yeah.
Yes, sir. Actually, operator matrix we are using, sir. Operator matrix. Yeah. So, actually, we are representing the operator matrix with the help of projection operators.
Operators. Yes. Okay.
And out of those operators, like X transpose and Y transpose. Only these two are orthogonal, sir. In
That's
two
right.
dimension.
XYT is also orthogonal.
Yes, sir.
See, but
Yes, sir.
XYT, if you do that, for example, okay, that's a good question. I think I know what the question is now. Let me share it. Okay. So, what you are saying, if I understand, let me erase this. It seems like I have frozen this page. Anyway, never mind. We'll go to one more page. Okay. So you said X is 1, 0. For example, Y is 0, 1. Your idea is that XXT is a projection operator, right? Sorry, XXT is an operator which is, yeah, it's a projection operator. 1, 0.
Yes.
Which is 1, 0, 0, 0. Correct?
Yes.
Now, what is XYT?
Yes, sir.
XYT is 1, 0.
Yes.
Sorry, XYT is, this has to be changed. Yeah. XYT will be 1, 0, 0, 1. Is that right?
Yes, sir.
Which will give you, what will you get? 1, 0, 1, 0, 0.
0.
Okay. Now you take the XYT square, what will you get?
Okay.
Multiplied by XYT. What will you get? Tell me. This is, first row is 0, isn't it? First element.
0. Yes.
Second one is 0, right?
Yes. Yes.
Third is 0. Fourth is 0. It's not a projection operator.
Yes.
What it says is that if you projected something using Y of t, and then you projected using X, that the whole thing does not lead to a projection idea. Therefore, XYT square is not XYT, meaning that XYT is not a projection operator. It is required in the definition of the operators, because the operator, any 2 by 2 operator will contain 4 elements. As I said, A11, A12, A21, A22, right? This you can write in the form of A11 times 1000 plus A12 times 0100. This is what you call as the XYT. This is XXT, okay, plus A21 0010. I'm just expanding this. This will be X. This will be YXT. This will be YXT. Okay, and then you have A22 0001. Okay, this is YT. Now, obviously, the other two are not projection operators. Now, you go to a 3 by 3 matrix. If you do this, you have only 3 quantities: XXT, YYT, ZZT, right? Only 3.
Yes.
The sum of the 3 will be identity. Each one is a projection operator. Why do we need these things? XYT. This is there. It's not a question of needing. It is already there to tell you that the 2 by 2 matrix is given in terms of not only this 2 by 2 matrix and this 2 by 2 matrix, but also these two. So it is to provide a completeness to the basis set that we need to worry about all these quantities, but they are not projections. Projections are only along the diagonals.
Yes, sir.
Yeah.
Okay, sir. Okay, sir. Now it results.
Thank you. Yeah. Okay, any other? If not, we will sort of close this up. Okay, do you want a class online meeting again on Friday, or shall we do it next Friday? I think you will need some time to study.
Yes, sir. It will be better if we have this on the next week.
Next Friday. That's right. This is not on the 18th, but on the 25th.
True, sir.
We'll have it on 25th, but tell your friends to also come up. Those of you who are studying together, and if there are others whom you know. See, the class has, as of now, registered with 1,000 something, 100 and, what is the exact number, Raja? You were saying some number yesterday, today. Did you say that?
1336, sir.
1336, but we have with us about 6 of us. It doesn't matter. I think the 6 of us have good questions, and that's what is important. And clarity in learning, and by being able to speak to them and think about this thing is more important. But please tell others, send messages to others saying that this is a long class. I don't know how many connected in YouTube. Oh, there is one more connecting to audio. I'll just wait and see who is that. But if you don't have any questions, yes, we can formally close the session, but one person is connecting. I'll find out what he has as a question. Yeah, Tirumala Rao, you just connected. Are you there? Okay, he's not joining. Hello? So the others can, you can leave if you wish to, but then we will meet on next Friday, not in the coming Friday, okay? Think about this, and you have more questions, please write to them. And also you can write to it on the forum. I'll try and see how much I can also respond immediately on the forum, okay? The session should be useful to you in terms of clarifying some of your doubts, okay? Thank you. Have a good evening to all of you. Okay.
Thank you.
Thank you.
Thank you, sir.
Yeah, Dr. Tirumala Rao, you just joined. Are you able to speak? Connect? Hello? I don't have any audio from you, so I'm not able to hear you.
Hello, sir. Yes, sir. Sir, I'm Balaji, sir. Sir, Tirumala Rao, I think you need to activate join with your audio, sir. Click on the join with audio.
Yeah. Join with audio is always enabled.
No, yes, sir. Dr. B. Tirumala Rao, my microphone is not enabled yet.
Oh, I see. Okay. But now I'm able to hear you. Yeah, tell me. You have something to, you have some questions or you have some comments? Please go ahead. The session was just about over, but I'm holding because I saw you join. So I thought I will stay. Yeah. Are you able to follow the lectures? Are you using them? Hello? Balaji, what is the issue in terms of joining with the audio?
Yes, sir. Its microphone is not yet enabled, sir. You need to give access or something. So
that's the only thing. And have you? Oh, you only told me. You only told me that his audio is not connected. Yeah.
Yes, sir.
Can you write a small message, Dr. Tirumala Rao? Can you write a message? I will also reply to that. Your type. Okay. No, I'm not hearing from him. I think. Who can see your man? No. But this is Zoom is facilitated even in all smartphones, right?
Yes, sir. Yes, sir. It will work, sir. Just they need to give proper, access to it, sir.
Yeah. So maybe there is some problem with Dr. Tirumala Rao's connectivity, but so what should I do? Should I close the meeting now? It's
yes, sir. It's we can give a closing remarks. We can.
He's not able to connect, so I feel bad about that whole process.
Sir, Dr. Tirumala Rao, you can type also, sir. Please type a message in the chat so that we can understand whether you are facing any problem or not.
Hello? Please type the message if you have any. Otherwise, we welcome you, but then the session is about over. So I have just scheduled another one for Friday, the 25th of February. The next one. Okay? We'll have one every week from that point onwards, if it is necessary. Okay. So thank you. And so let me meet you again. If you have any questions, please feel free to either write to me. You have all my email ID, and you can also send it to my email ID if you wish. Oh, there is a new message. Yeah, what is the new message? Yes. Sir, what will be the format of projection operator matrix in spherical polar coordinates? Actually, for the matrix, we don't need the coordinates. Okay, if you are thinking about r, theta, phi as the basis coordinates, and you're right, I have to think about this as an answer. Can you give me some time, Sandeep?
Yes, sir. Yes, sir. Okay, sir. Okay, sir.
I'll answer this after looking through myself a little bit. The thing is that the coordinate space XYZ is an orthogonal coordinate space. Therefore, you can easily write down orthogonal projectors. Px, Py, Pz as xxt, Yt, zzt. The coordinates r, theta, phi are non-orthogonal. The unit vectors Er, E theta, and E phi are not orthogonal to each other. That's the reason why the hydrogen atom kinetic energy is a fully messed up quantity with so many quantities inside. Therefore, the projection operators will be non-orthogonal, and each one we'll have to look at. PR, what is the PR doing? PR may be an orthogonal, PR may be a projection operator, P theta will be a projection, P phi, but PR, P theta will not be zero, PR, P phi will not be zero. Therefore, the projection does not project everything out of the R space and leave the others outside. So there is no more to think about any theta. If you think about X and Y and Z, if you project vector A to the X-axis, the component AX has nothing to do with Y and Z. It's orthogonal to AY and AZ, that component. Therefore, once you project A using X-axis, if you try to project that quantity on the Y-axis, if you project AX on the Y-axis, it's zero. That's what is called the orthogonal projection. Whereas in the r, theta, phi, they are not orthogonal. Therefore, there may be residuals. If you try to project a function r, theta, phi using PR, the function may have theta and phi dependence. And therefore, if you try to do using p theta, you will also get some value. This is what I can immediately think about, but let me put these things down in a formal way so that you can have an answer. Okay?
Okay, sir. Okay, sir.
Thank you. Okay, Balaji, we can probably close. I think Dr. Tirumala Rao, yeah, he's still there, but I'm not able to see anything or hear anything from